Chem 1 lecture over Half-Life. So we'll start with a little funny comic here. Half-Life says, I will see you will have a long and prosperous half-life, as opposed to just life, because it's an atom getting its... Anyways, who cares? What half-life is it's the time required for one half of the atoms of a radioactive isotope to emit the radiation and decay into their new isotopes. And I have another one that has the definition to this slide right here. I think it might match better. But half-life is basically how long it takes if you have 100 atoms of radioactive plutonium to decompose and inject that alpha particle and become uranium. So if I have 100 of them, half of them would be 50. So when there's 50 left that are still plutonium, how long did it take me to do that? And if there were 50 of them, half of that is 25. So how long did it take for it to be 25? And it's actually a constant number. So this is a graph showing half-life. You can see it's exponential, so it's going to decrease and approach zero. Eventually, they will all decay, but that's a while down the road. So if I start with 50, what is half of 50? 25, which is right here. So you can figure out the half-life from a graph by looking how long did it take to go from 50 to 25. And in this case, it was about 25 days. Just randomly, it happened to be the same. Now, if you started with another number, let's say we started with 25, half of that is 12.5. It should take the exact same amount of time, again, 25 days, to decay by half again, and so on and so on and so on and so on. Tomorrow, you're going to do a lab where you find the half-life of my favorite radioactive candy, M&Ms. They're not really radioactive, but we pretend that the M side is radioactive and the non-M side is stable. So you shake them, dump them out, and we're going to get a nice pretty graph, and you're going to be able to determine the half-life of an M&M. The stability of a radioactive isotope, or a radioisotope, is the same thing, is indicated by its half-life. The longer the half-life is of something, the more stable it is. And I told you those products of fission create two very stable, which means they have long half-lives, radioactive byproducts. So that kryptonium and that barium hang around for a really long time before they undergo decay and become something safer that's non-radioactive. Half-lives can vary from a fraction of a second to years and years and years and years. It just depends on how stable that nucleus is. Your artificially produced isotopes have very, very short half-lives. On my periodic table, if you guys remember it when it was hung, black are solids, blues are liquids, reds are gases, and people are like, well, what are the white ones, Miss Nelson? The white ones are your man-made elements. These don't exist naturally in nature. They're made with super colliders and things like that, smashing big atoms together, and then they break apart and undergo this radioactive decay. Carbon-14 dating. If it wasn't for carbon, I wouldn't date at all. It's a little joke, a little chemistry humor for you guys. Carbon-14, there's three main isotopes of carbon. Carbon-12, 13, and 14. 14 is in very small amounts, and it's radioactive. It'll undergo beta emission to become nitrogen. Basically what happens is nitrogen in the air will gain a proton, become carbon. Plants breathe that carbon in, turn that carbon that's part of carbon dioxide into glucose. We eat the glucose, we die, we have that carbon-14 in our body. Well, once we pass away, or once any living thing passes away, it stops taking in new carbon-14. So the carbon-14 that you do have starts to undergo that beta emission and become nitrogen. So you can determine the percentage that you started with and the percentage you have now and determine how old something is, because we know the half-life of carbon-14 is 5,730 years. So it's a very stable nucleus, and because it for so many years, we can date things back that are very, 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 very old. And so there's that process I was telling you about. The neutron right here bombarding with the proton, nitrogen, releasing that proton, becoming carbon-14, getting taken in by the plants as carbon dioxide, getting eaten by the animals, and then when the animals die, it starts to decay back to nitrogen. And then the bacteria in the ground take that nitrogen, put it back in the air as nitrogen, and the whole process happens over and over again. So that's kind of neat in itself right there. So you say our dates last forever, but I can prove otherwise by measuring the breakdown of a common element, carbon dating. Get it? Carbon dating since 19... They're pretty funny. I agree. So how do we calculate half-life? There are 5 variables involved in a half-life problem. M sub O is the original mass you started with. N sub T is the mass after a specific amount of time. T is that specific amount of time. T sub 1/2 is the exact half-life. And N is the number of half-lives that have happened. N will always be a whole number. So if the half-life is 20 years and 100 years has gone by, how many half-lives have passed? 100 years have gone by, the half-life's 20 years. How many half-lives have happened? 5. So N would be 5. It's the number of half-lives that can fit into that. There's 2 formulas. Both of these formulas will be given to you on the quiz, which is on Monday, and the test, which is next Wednesday, a week from today. The number of half-lives equal the time that's passed divided by the length of the half-life, and the amount after this amount of time is equal to the amount originally divided by 2 raised to the number of half-lives. This is a raised 2, so make sure when you copy that down, you make it look like an exponent somehow. Again, these formulas will be given to you. Every half-life problem, you have to use both of them. Sometimes you might start with this one, go to that one. Sometimes you might start with that one, go to this one. Whatever you're looking for, like let's say you're looking for the amount that's left after a certain amount of time, whatever formula you're looking for has the variable you're looking for is going to be the formula you use second. So if you're looking for this, you're going to have to use this formula first and then this one, kind of thing. And we're going to do 3 practice problems right now, and you're going to realize that these are pretty easy peasy. I'm going to show you the only ways I can possibly complicate this, and then you guys can start working on your homework. So, what mass of an isotope remains after 10.5 years if you start with 25 grams and the half-life of this isotope is 3.5 years? So, how much remains? So we're looking for M sub T. That's what we don't know. Here is our amount of time. Here's our original mass. And here is our half-life. So again, you'll be given 3 of those 5 variables. We have T and we have T sub half. So I'm going to use that formula first. N equals T over T 1/2. Time is 10.5 years. Half-life is 3.5 years. How many half-lives would have happened? 3. Good job. So that's the number of half-lives that have happened. Now that I know N, I can go use the other formula. M sub T equals M sub O, which is 25 grams, over 2 to the nth, which is 3. Let me write that formula that I used just so you have it in your notes. M sub O over 2 to the nth. And then I just plugged N sub O in and N in. So that's basically 25 divided by 8. So the amount that would remain is 3.125 grams. The only thing that's tricky is you got 2 formulas. You just got to know which one to use first in that problem. Let's do another practice problem. This one says, how long would it take a sample to decay to 12.5% of its original mass if the half-life is 500 years? So what we're looking for is how long. We're looking for time. We have T 1/2. But look, they don't give us an M sub O and an M sub T. Here's my best advice to you. Percents are out of what? 100. So if you see a percent problem, and again, you can really take any number and make the M sub T 12.5% of it. But what I like to do is say, okay, well, since it's out of 100, I'm going to pretend that I started with 100 grams. What's 12.5% of 100? 12.5 grams. Any of numbers would do there. You could say there's 1 gram, you could 34 grams, and then just find 12.5% of it. The only way I'll trick you with percents is sometimes it'll say, how long does it take for it to lose 75%? So what percentage are you really using? If it's losing 75%, you actually have 25% remaining. So watch out, because this one says you have 25% remaining, 12.5% remaining. But if it said lose, what is that, 82.5, then you would say, okay, there's 12.5%. So just look at the words around the numbers. Always be doing that. Okay, so I'm going to obviously use this formula first this time. And so my MT is 12.5 grams. My MO is 100 grams over 2 to the nth. N is my unknown variable. It's in the denominator. Whenever you have an unknown in the denominator, get it out of there. Times 2 to the nth times 2 to the nth. So I got 12.5 times 2 to the nth equals 100. We're trying to isolate that in. So 12.5, 12.5, 2 to the nth equals 8. Whew. At this point, there are 3 different ways that I can suggest that you solve this problem. The easiest way, the way I like to do it personally, is I use my fingers. I know, it's very, very, very scientific. I say 2 times 2 is 8. How many 2's did I have? 3. So what is n going to be here to make it equal 8? 3. Or take your calculators that you have out and say 2 raised to the 1 equals 2 raised to the 2 equals 2 raised to the 3 equals 2 raised to the 4 equals 2 raised to the 5 equals, until you get it to equal what you want it to equal. Because you know n's going to be a whole number. It's never going to be like 2.684. It's going to be a whole number, so you can just kind of test. Maybe on your quiz, you do that when you begin. 2 raised to the 1, write it down 2. 2 raised to the 2, write down 4. And you make a little chart in the top right-hand corner so you can just reference it as you solve Half-Life problems. Or you could do it the mathematical way. When you have something to an exponent, what you can do is take the log of both sides. When you take the log of an exponent, it's the same thing as multiplying by that exponent. So log of 2 to the nth is the same thing as n log of 2. And then you can just divide both sides by log of 2. So in your calculator, if you type log 8, close parentheses, divided by log 2, close parentheses, you should get 3. Huh? Yes, yes. You've done Half-Life before. I told you this before we started this lecture. I actually teach it easier. This is not super difficult. If you want to do it that way, fine. None of them are ever really super high. I think counting my fingers using my calculator works just as good. But if you ever get stuck, this method is there for you. All right, but we're not done with this problem yet. Oh, you want me to go back down? We're not done yet, though. We still have the other formula to use. I know that seemed like a lot, but that's just because I was showing you a bunch of different methods. Know that n equals 3, so we're going to use the formula n equals t over t 1/2. N is 3. T we don't know. T 1/2 was 500 years. So t equals 1,500 years. So that's how long it would take if the half-life was 500 years to decompose to 12.5% of its original amount. We're going to do one more practice problem. And the only reason I'm showing you this one is because, like how this one was a little bit different with the percent, this next one's a little bit different with a fraction. So it says if only 1/32 of an original sample remains after 30 years, what is the half-life? So here is my time. We're looking for t 1/2, so I know I'm not going to use that t over t 1/2 formula first. I'm going to have to use the other one. I need to know what my m sub o and my m sub t is. Now, just like I said, a percentage out of 100, a whole fraction is equal to 1. So I like to do this, 1 and 1/32. Makes my life easy. So m sub t equals m sub o over 2 to the nth. N sub t is 1 over 32. This is 1 over 2 to the nth. What do you think 2 to the n equals to? Look at that, what I just plugged in. 2 to the nth equals what? 32. Do you see how it's a fraction 1 over 32, 1 over 2 to the nth? You could just set the bottom parts equal to each other. They're both 1 over. See how sweet that deal is? Now we'll do my finger method. 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2, 32. How many n's are there? N equals 5. Or you could take the log of 32 divided by the log of 2. You're also going to get 5. N equals t over t 1/2. N is 5. T is 30 years. When we're looking for t 1/2, our unknown is in our denominator, so multiply it. Get it out of that denominator as quick as you can. And t 1/2 is going to equal 6 years. The only other way I can trick you is I give you like the half-life in years and the time in days. You got to make sure that your time units are the same and that your mass units are the same. So days, minutes, seconds, it doesn't matter as long as they match.